That's another issue. Let's try to get the visual first.
Okay, yeah.
Was it not on before?
I don't know.
I wasn't picking up very much, so that's why I don't know.
Okay. It's on. Okay, can you hear the mic?
Yeah, we're good.
Okay.
This is on. Sort of. Don't mess with it. It's just very. It's just.
It's becoming brighter, right?
Yeah.
Yeah.
There we go.
Okay. All right. Yeah. So, kind of in, yeah. So, most or all methods that had kind of rigorous statistical guarantees on the output were based on convex relaxation, which is that you kind of relax the rank constraint to be either a trace norm if it's positive definite or a nuclear norm constraint, with the idea that this is a convex surrogate for this. Okay. This is, and meanwhile, what used to happen in practice is that, I mean, especially for larger scale problems, you would actually explicitly encode the low rank matrix in terms of two much smaller matrices. So you would kind of obtain something like this, which you want to minimize the function over UV transpose, and then you would employ some kind of local descent methods on the non-convex form. Right? So this is solving a non-convex problem, typically just from a random initialization, and it's not a priori clear, you know, if you'll get a good statistic, if the final output will be good or bad, right? And so what my work has been is to kind of bridge this gap by seeing that there is statistical assumptions assumed on F. So one thing to note, this is not tractable in general, and it's not tractable even for nice convex functions, right? It's very easy to come up with examples where even among classes of convex functions or even subclasses of them, you may not be able to solve this problem exactly. Right? So what often happens is that there are statistical assumptions on the data, and that is equivalent to saying that there are some assumptions on F, and under those assumptions, convex optimization is shown to perform well. Right? And so the natural question that arises from this picture is, if we took pretty much the same assumptions and thought about the more efficient algorithm, what would happen, right? Can we get the best of both worlds in some way? Okay, so I'm just going to go over two examples of this. So the first problem is matrix completion, right? And I think almost everybody, if not everybody in the room, knows what matrix completion is. It's that you have a low rank matrix, you see a few elements of the matrix, and you want to figure out the full matrix, right? So the first theory or rigorous method for this was the famous paper by Candace and Recht from, I guess, 7 years ago now. And what they did is that they want to find a low rank matrix which matches the elements that are observed, right? So for all elements that are observed, my unknown matrix should be equal to what I observe, right? And then I want to minimize the rank, but minimizing rank is not a convex object, and so they instead minimize the trace norm. Okay, and just to paraphrase the result, I mean, this is a pretty famous result, is if the matrix is incoherent and sampled uniformly at random, then this procedure will exactly recover the matrix from nr log n or nr poly log n samples. Right? So I've phrased it as an if and then to make it clear that these are that the first line is the statistical assumptions they put on the model in the data. And then they have a result which is a kind of near optimal number of samples to recover the matrix. All right, so this is great, but what is the drawback? So the drawback is primarily computational, right? If you'll notice here, the size of the data, right? What is the data you're given? It's elements of the matrix. that's of size essentially NR. I'm going to ignore logs, okay, for now. So the data is of size NR, right? And R is something that's much smaller than N, typically, right? The rank is much smaller than N. The output is of size NR because it's, you could think of it as just two matrices U and V, and each is of size NR. Yeah, so we have kind of small data, we have small output, but it becomes a big problem because of the parameterization, right? We have an order n square matrix, right? So if you were to solve this using, for example, projected gradient descent or something, in intermediate steps you would get pretty high rank matrices, right? And so even though the ultimate output is low rank, and maybe even your initialization is low rank, right? It's really, if you want to exactly solve this convex problem, there is no getting around the fact that intermediate steps will have high rank matrices, and you'll have to take spectral, you'll have to do eigenvector computations of them, right? Okay. So this is one example where what I just said about this disconnect between theory and practice happens, right? So this is a great method in theory, and it has this issue from a computational perspective. All right, so matrix completion also is pretty popular in industry, primarily due to its connection to collaborative filtering or recommendations. And large-scale problems there are typically solved by alternating minimization or gradient descent on a non-convex form. Right? So what they do is, what's kind of shown here is that you explicitly keep track of variables u and v, and you just minimize a natural loss function, which could be this or this plus some regularizer. So this is just a squared error on the elements you observe. Right? And you can, and so now this can be solved using either alternating least squares or alternative minimization. So what is that? That is that if you keep u fixed, this is just least squares in V, and if you keep V fixed, this is least squares in U, and so you can keep alternating, and in this case for each step it's pretty much closed form, so it could be pretty fast. Other popular methods are stochastic gradient descent on U and V, so which means you observe an element and you update the corresponding UI and Vj and keep doing this. So that's another example. So this is empirically popular. Now what was somewhat surprising, at least to me when I started looking at this, is that besides the fact that it's faster, that was kind of clear a priori, it often requires a lower number of samples. Right? So if we just, even if we do not care about computation and we just look at it from a statistical perspective and compare the two algorithms of convex optimization and alternating minimization, this is a simple example on like 1,000 by 1,000 matrix of rank 5 or something, right? And we just look at the number of samples we need before like 95% of the instances we recover the correct low rank matrix, and we need fewer samples with alternating minimization. Right? So not only is it computationally better, it is statistically better. Right? And so clearly there is some value in understanding what is happening with these non-convex methods. All right, here's another problem with in the same theme, but it's a slightly different problem. Okay, so this is the problem of phase recovery. So what this problem is that you want to recover an unknown complex vector, and you get what should have been linear measurements, except that you see only the magnitude and not the sign. It's called phase recovery because in typical applications everything is complex, right? So x is an unknown vector, but it's a complex vector, and a could also be complex, right? So a is your measurement matrix, right? So simple linear measurements would be y equal to ax star, but you do not get the phases, you only get the magnitudes, right? So you get your measurement matrix and you get the magnitudes from the unknown vector, and the task is to recover the unknown vector. And clearly this is clearly you can only recover up to global phase, right? Because if I change every element of X star by the same phase, then it's not recovered. All right. So this is an abstraction of a problem that arises in diffraction imaging. So let me show you a toy example that's kind of fun, which illustrates that phase matters. So let's take these two simple images, right? One is a cat and one is a duck, and take its 2D Fourier transform, right? So the magnitudes look something like this. The phases look something like this. The magnitudes are something else. Okay, now what I'm going to do is I'm going to mix these images up. So I'm going to keep the magnitudes, right? But I'm going to switch the phases. Okay, so a Fourier transform, gives complex numbers. There's a magnitude and a phase for every pixel. So I'm going to keep the magnitudes the same, but I'm going to switch the phases. Okay, so I get something else. And now I take the inverse Fourier transform.
So what are you plotting? Is it the phase or is it the magnitude?
This is the phase. This is the phase.
So if it's a phase and then you switch the phases, why don't they just look the same?
Why don't they look the same?
The magnitudes are the same.
No. So when I take the Fourier transform of this, right? So every element here, imagine is a complex number. In this case, it's real. But when I take the Fourier transform, then there's a magnitude and a phase for every pixel. Now, what I do is I mix them up. So for every pixel here, I keep the magnitude from the cat, and I keep the phase from the.
Plotting the phase.
Yeah.
Then we switch the phase.
Yeah.
Then the bottom left and the top right should look the same.
Yeah. So this should look the same as this. It does not look the same?
It's not the same.
Okay. Then maybe it's a different plot of the complex numbers. There's a way to plot complex numbers in MATLAB, so maybe it's not exactly that. But this is what we did. I don't know what this thing is plotted. So I don't know what these are exactly, but what we did was to switch the phases while keeping the magnitudes. And what you can see is that this looks pretty close to being a duck, and this looks pretty close to being a cat. Right? So really the information in these images is pretty much captured, is I would say more captured by the phase than by the magnitude. So phase is important, right? In many applications, especially when you're doing sensing. All right. So it's not my objective to get into the phase recovery problem. That's a talk from 2 years ago. So I'll just quickly say, so the first rigorous method, in the sense of giving performance guarantees under statistical assumptions, was again based on convex optimization. And so what they did is, so recall that yi is the magnitude of the inner product of ai and x. So yi square is ai x ai. Right? And now you take the XX transpose, and that's it's the outer product of a vector with itself, and you can just imagine making that a matrix of rank n by n, making that an n by n matrix, and it should be rank 1. Right? If you try to write an optimization problem with the rank 1 constraint, that's a non-convex problem, so you drop the rank constraint. So this is exactly the constraint that what you are measuring is what that it should satisfy, that x should satisfy the measurements, right? X should be positive definite because it's the outer product of two vectors. If I want to solve the problem exactly, I take these constraints and I add a constraint of x being rank 1 and just try to find a feasible point. But now for convex relaxation, what they did is they removed the rank 1 constraint and instead put a trace norm penalty, with the idea that a trace norm penalty encourages rank 1 solutions or low rank solutions. And that's exactly what they showed, and I again paraphrase the statement in an if-then way. So if my measurements come from standard Gaussian, complex standard Gaussian, then convex optimization exactly recovers the original vector up to global phase, right? So what that means is that you can recover the outer product exactly, right? But you cannot recover the phase from order n samples. right? And order n is optimal.
The outer product doesn't give you the phases back, right?
I mean, it gives you it gives the relative phases, but not the global phase, and that anyway it's probably you cannot get it, right? So, all right. Okay, so and this has the same drawback, right? We initially had an order n problem. We want to find a vector, and instead we are optimizing over matrices which are an order n square space. Right? Okay, what was empirically popular? So this is a classical problem that predates convex analysis. That predates convex analysis of that problem. And so the most popular approach by Gershberg and Saxton was essentially the application of the EM algorithm to this problem. Right? So what that says is you can write this as a non-convex problem where, okay, so y is equal to the magnitude of AX. But if you knew the phases, right, then you could make a diagonal matrix of phases, let's call it C, right, and then Cy would be equal to AX, right? So now, but the problem is we don't know the phases, right? So what we can do is we can just have that as a variable and just minimize over C and X of Cy minus AX, right? So C is a diagonal matrix of phases and X is your unknown vector. Right, and you do this minimization, and this is not a convex problem because C has to be phases, right, and that's a non-convex constraint. All right, but you can still do alternating minimization pretty easily, in the sense that if you fix C, this is a least squares problem, and if you fix X, then the way I'll find C is I'll look at each equation and I'll find the best phase of I'll find the phase of the right hand side and keep that as the phase of the left hand side. Right, trivial. Okay, so alternating minimization is easy. It turns out this is the EM algorithm for this problem, and that is what has been empirically popular. Right, so what happens in practice is you have a bunch of other extra constraints, and so you also incorporate those constraints. Right, but at the simplest level, this is what is happening. All right, so we again have the same story from a statistical perspective, right? So this is clearly a faster algorithm than convex optimization, right? At least on a per iteration basis. Every iteration is faster, right? It was not known whether how it worked, but it worked well in practice, right? And if you do a small simulation, you again get the same behavior, which is that it actually needs a smaller number of measurements than convex optimization, right? So even from a purely statistical perspective, it performed better than convex optimization. All right. So other problems in the same flavor, and I'm not going to go into too many details, into as much detail. So one is the problem of matrix regression, where you want to fit a low rank matrix to data, which you can rephrase as solving a bunch of linear equations where the variable is a low rank matrix. Okay. So it could be measurements of the form X inner product with some other unknown measurement, with a known measurement matrix, or you could have the observations being essentially rank 1. Right? So you have some vector AI which you know, and you know yi. So this is a generalization of phase retrieval. Okay, and we also looked at mixed linear regression, which is the problem where, okay, so solving linear equations is you have an unknown vector and you get a bunch of linear equations and you want to solve them. Mixed linear regression is, in the noiseless case, is solving linear equations, except that there are two unknown vectors and every observation is either from beta 0 or beta 1. And given these, but they are unlabeled, and given this unlabeled collection, you have to find out both beta 0 and beta 1. Okay, so to summarize, a recurring theme has been that in theory we have convex optimization and some statistical assumptions, and we get performance guarantees, but this carries a computational cost. right? So the natural question is, does this happen because there is something great about convex optimization, or does this happen because the statistical assumptions made our problem easy? Or another way of saying it is there any algorithmic value in doing convex optimization for these problems? Right? So doing a few simple experiments to compare one versus the other, it does seem that statistical assumptions do make the problem easy, in the sense that even the non-convex methods seem to perform well. Right? So what we have been trying to do is to rigorously show that this is the case. I mean, I'm not going to go over this slide, but we did look at the 3 problems, at the 4 problems I mentioned, along with several people in the audience. So pretty much the theme here is that the statistical assumptions under which convex optimization was known to provide good solutions are pretty similar to the ones under which popular non-convex methods, popular and much faster non-convex methods can also provide good solutions. Okay. So I want to go a little bit in. What I've been doing more recently with Srinath and Tasos is to get a kind of more general understanding of what is going on in all of these problems. We do not have a full general understanding, so this is like preliminary work. As you will see from the slides, they look pretty rough. But you know, I'm local and I'll be happy to discuss. Okay, so we looked at the setting of semi-definite optimization. Okay, so this is where you want to minimize a nice convex function over the set of matrices which are positive definite. Okay, this is related to semi-definite programming, but semi-definite programming is a little different. In semi-definite programming, your objective is linear and you have linear constraints as well. Right? While we are looking at the case where the objective is more generally convex and we do not have any extra constraints right now. Okay, so you know, this problem is already tractable. There are many ways you can solve this. One natural method is projected gradient descent. So that's the case where, okay, so if you just want to minimize a function which is convex, you would do gradient descent. Right, now we have an extra constraint, so you do projected gradient descent. What that means is you start from a point which is feasible, which means it's positive definite. You take a step in the gradient direction. If your new vector is still positive definite, then don't do anything. If your new matrix, and if your new matrix is not positive definite, then project it onto the positive definite cone. And basically what that means is find its eigenvalues, or find all its positive eigenvalues, ignore all the negative eigenvalues and corresponding negative eigenvectors, right? And you will get a new matrix that is positive definite, and you can keep doing this.
Is it necessarily going to stay symmetric so it has eigenvalues?
Sorry?
Is it necessarily going to stay symmetric when you do this now?
Yeah, so we are going to assume f is symmetric, and so the gradient is symmetric, and yeah, so I should have said convex and symmetric f. Yeah. All right. Right. So 2 points to note about projected gradient descent. So first is it assumes something about the method, right? So it's it uses what is called first order oracle access to f, right? Which means that what is this f, right? If f is some special function and I know the form of this function, then maybe I can do much better than gradient descent, right? So but if you want to think of a general purpose method, then a common way that people think about it is via oracle access, right? So a zeroth order oracle access would be that I tell you my x and you tell me the value of f, right? So that's zeroth order oracle. That's the simplest one, right? Where I don't know anything about f beyond this black box where I give an x and I get a value of f, and I get the value fx. First order oracle is that I give a value x and I get the value of the function and also the value of its gradient. right? And that's the only way I access the function. All right. In our work, we are also going to assume first order oracle access to f. Okay. The other thing going on here is the projection step onto the positive semi-definite con. Right? Now, this could get computationally intensive once you get to larger size matrices, right? Because you have to take kind of an SVD at every step. And an SVD at every step could be computationally intensive. Right? Okay, so what is our approach? So so it's based on the observation that X is positive definite if and only if there exists some matrix. In general, it is also n by n, such that X is UU transpose. Right? So if you can write X as UU, so X is positive semi-definite if and only if you can write it as UU transpose for some u. So the original problem is exactly equivalent to this problem, which is f of UU transpose. Okay. So this is what we'd call a Schmonvex function, right? It was formerly convex, but now it's non-convex, but for a very specific reason. Right? I just replaced X with UU transpose. And now, once we have this, you can just call this function g of u, and it's a non-convex function of u, but you can do gradient descent. Right? So that's what we call, I guess, factored gradient descent. And what that is that you update u based on the gradient of g of u. Right? So where g of u is f of UU transpose. And that just turns out to be this. Right? So it's u minus eta times the gradient of f times u. Right? So conveniently, this still needs only first order oracle access to f. And there is no projection step. Right? This is just gradient descent. Okay, we're going to push even further, and we're going to say that we're going to artificially restrict U to be an n by r matrix, right? So the original problem was equivalent to minimizing f over UU transpose, where U is an n by n matrix. So we have got one win, which is we don't need to do SVDs. We don't need to find eigenvectors at every step. But we are still dealing with a pretty large matrix, right? We haven't got a reduction in the size of the problem, the size of the number of variables. So what we're going to do is we're going to artificially restrict U to be an n by r matrix. Right? So now this is not equivalent to the original problem, but hopefully we can get some kind of approximation. Right? So there are two reasons why this may be good to do. There is the statistical reason, which is kind of the reason why low rank matrices are popular in machine learning, which is that you will not overfit your data. Right? If you take a matrix completion problem, say that comes from an actual recommendation data set, there is not going to be an exact fit with a low rank matrix. Right? So low rank matrices are chosen so as not to overfit. And also the other reason obviously is, as I mentioned, computational, because if you have a smaller u, it is faster. Right? So the main step here is a matrix vector multiply between the gradient and u, and so this becomes faster if u is smaller. And also in several cases the gradient itself may be faster to calculate if your u is low rank. So just imagine matrix completion. The gradient will be faster, even just computing the gradient will be faster if you're computing it at a low rank matrix, and I give you the factored form of the low rank matrix. Okay, so we're going to try to understand this kind of algorithm, which is artificially restricted, right? And as a special case, we can recover r equal to n, and that's the original problem. Okay, so let's rewind a little bit and refresh our convex optimization. So we're going to first consider the simplest case where f is strongly convex. Right? So f is a strongly convex function of n by n symmetric matrices, or the n by n symmetric positive definite matrices. And so this is what is happening if you just look at X space. right? So the overall ambient space. A strongly convex function has level sets that look like this, right? So I've drawn a contour plot of f. If you do gradient descent, right, it will converge to the optimum, right? So this is gradient descent on x. Right? This is a naive problem, and I've even ignored for now the positive definite stuff, right? It's just minimizing f of x, f being strongly convex. Right? So you get something that looks like this. Now, one thing to note is, so the natural question is, it is known that we'll get to the optimum, and it's also known how fast we'll get there. And how fast we'll get there depends on the condition number of f, right? So if you look at the Hessian of f, and you look at its minimum, this is positive definite because it's convex, and so it has a minimum and maximum eigenvalue. And so so there are two things that matter. One is that we need to choose a good step size, which is 1 divided by the maximum value, the maximum eigenvalue of the Hessian, right? If you have an eta that's bigger than this, it could overshoot, right? So if I take a gradient step, it could go on the other side, and then I could take a gradient step and go even further. So if you take a big step size, it can even gradient descent can overshoot. So your step size should not be too big. And how big is big? 1 by m. Right? 1 divided by the maximum eigenvalue of the Hessian. Once you do this, then the error decreases by a factor of 1 minus 1 by kappa, where kappa is the condition number. So condition number is uppercase m divided by lowercase m. Right? So if you have a good step size, you can get a multiplicative decrease in error in every iteration. Right? So you converge geometrically fast to the optimum. And how fast you converge depends on the condition number. Okay, so this is for standard strongly convex f. Okay, so now let's look at what happens in the non-convex case. Right? So I've taken a strongly convex function, and I've just made it, and so here u is just vector of length 2, right, for illustration purposes. Right? And so even though I have a strongly convex function, this is non-convex, and the non-convexity is exactly of this type. Right? So this is u, and the two dimensions of u, and we see that there are two optima, right? Even though f is only one optima, and these two optima are actually the same optima. They are just u star and minus u star. Okay. So getting to any one of these is fine, right? But it shows, when you think of it from an analysis perspective, it shows what is the issue, because it shows one of the issues, which is that there are multiple optima, right? In the vector in the rank 1 case, you could have plus u star and minus u star. But if you have a rank 5, then you could actually have rotation matrices in between them. And so you would have like a whole continuum of optima. Right? Okay. But this also shows that there is some hope, right? In the sense that around each optimum, there is a local region of convexity in this case. Right? More generally, if you have a continuum of optima, you'll have what looks like a valley. And all you need to do is get to the bottom of the valley, and any point on the bottom is fine. Right? It's hard to show that on a two-dimensional surface, but you can imagine that's what's happening. All right. So let's look at a specific function, which is minimizing over a vector u. So I'm restricting R to be rank 1 of m minus u transpose. But M is a general matrix of M is a general n by n symmetric positive definite matrix. Okay. So you would expect the optimum of this to be the top eigenvector, right? Or the eigenvector corresponding to the most positive eigenvalue. Okay. Gradient descent is this. Right? So this thing is the gradient, and so this is gradient descent. And so the question is, what step size do we choose, right? So in this case, we can just calculate, right? And so we'll see that, so if we take this as a function of u, so that's g of u, and take the Hessian, it looks like this, right? It's pretty easy to compute. And so the maximum eigenvalue of this thing, okay, so this is the function and the maximum eigenvalue is something. Now let's imagine that u is close to the optimum already, right? So which means if you look at the picture before, what are we trying to show? What do we hope to prove, right? So what would be awesome to show is that no matter where you start, you might wander around a little bit and get into a valley, right? This is empirically observed, right? It would be very interesting if somebody could actually prove something like this, but we don't have a proof of that, right? Instead, what we do have is that once you get into a local region of local convexity, it's not really convexity because when you have a continuum of optima, it's not locally convex even then, right? But once you get kind of close to the optimum contour, then you will get to the optimum contour, right? That's what we show. And even that is not immediate. You need to be a little bit careful about the step size. So I'll just tell you what the step size needs to be for this specific problem. Alright, so this is the problem, gradient descent. We looked at the Hessian. Now we just go back to what we know from convex optimization, and we say, it should be less than the top eigenvalue of the Hessian. If it's not less than top eigenvalue of the Hessian, you may have the issue of overshooting and never getting down and not actually descending, right? So what is the maximum eigenvalue of the Hessian? Where the thing is, here the Hessian depends on u, right? And so there is no uniform max eigenvalue, right? In spite of the fact that if you think of this as a function of x, it has a max eigenvalue, the Hessian. But once you parameterize it as u, there is no real max eigenvalue, right? But we only want a local analysis. So imagine that u is close to u star, where u star is the eigenvector, is the eigenvector corresponding to the most positive eigenvalue times the square root of that eigenvalue. So that u star transpose is the best, is the optimum. Okay. So if you have that, then the maximum eigenvalue is close to 2 times the norm of u square. Right, so to see that, if this was actually the top eigenvector, then this would be 2 times the top eigenvalue plus the top eigenvalue again minus the top eigenvalue. That would be the top eigenvector of this thing. Right? So in the u1, you'd have 2 u1 transpose times lambda 1 plus lambda 1 for everybody minus m, and m has a minus lambda 1 in that, right? So it's a pretty simple calculation, and it's not hard to see that the top eigenvector of, if this was exactly u1, then the top eigenvector of this would also be u1, and the top eigenvalue would be 2 times lambda 1, right? So this is locally, so which means if u is close to u1, then this is also close to that, right? So this means that you should choose a step size which is 1 divided by modulus. Right? So we need an adaptive step size. Okay, so does adaptive step size matter? So it turns out it does matter. Right? So here we see several plots of what happens when you choose fixed step sizes and when you choose an adaptive step size. Okay, and this is the log error between u and u star.
But if you only care about the local convergence, that isn't the norm of u basically constant within that local region?
The norm of u is basically, yeah, so this is from a random initialization.
Okay. But like, shouldn't you be able to choose whatever the norm of u is, and then at least at the end it should be converging at the same rate?
Right. Yeah. So you could always choose an oracle u, and an oracle step size That's what you're saying, right? Not Oracle, I would say Gini step size.
Yeah, sure.
There is some Gini step size. Yeah, so if I chose the best step size and I was close to U, then I would converge at the same rate as this. That's right. But this gets there without requiring that Gini. Okay. So for that special function of M minus UU transpose, we can actually show that with this step size, you will linearly converge to V1 from any initial point that is not orthogonal to V1. Okay, so we don't really need some smart initialization, but that's for this very special function, right? And for this very special function by itself, this method is not interesting because that is just finding top eigenvector, and there are like infinitely faster methods to do that, right? So for more general f, we need to initialize properly, right? So we'll not really get into the initialization issue right now, and but first look at what happens if you can initialize properly. Right? So if you can initialize properly, then like if we initialize here, then we can actually show, and that's kind of our main result, that you will linearly converge to the optimum, even in the non-convex case. Right? And how close this close need to be? You need to be a constant distance away. Right? So U minus U0 divided by U should be a constant.
Is it locally non-convex?
Yeah, it is locally non-convex. I mean, as I said, I cannot show it here because I can only show a 2 by 2 and rank 2. But if you imagine if I had a rank 4 matrix, then so let's say U is optimum, then U times the rotation matrix is also optimum, and so I have a contour of optimality, and that contour itself is non-convex, right? So if I have a function whose minimum is a non-convex set, then that function is non-convex. So it is locally non-convex. Okay. Here's a simple plot of error with initialization and without initialization. And as I said, I mean, empirically, it's very hard to construct an example where you need initialization for it to actually work. But a proof of that, eludes us. Okay, I'm going to skip forward in the interest of time. Okay, so.
Construct an example, but has that been done?
Sorry?
You say it's hard to construct an example where it doesn't work.
Yeah, okay. Okay. It's hard to construct a statistical setting. Okay, so yeah, it's not like I've tried to construct one, but most statistical settings I see, or simulate, it seems to work from random initialization, right? Yeah. I mean, there's no hope of a worst case statement here anyway, right? But there's hope of a positive statement in the statistical setting from random initialization.
All other examples where the convex method works and alternate initialization for random start does not work.
That's a good question. Yeah, that would be a good way to phrase it. I'm not sure. Okay, so this is factor gradient descent. Yeah, sorry.
So actually, for general non-convex problems, we do simple gradient descent, but directly is that if you converge to the local minimum, right?
Yes.
So by choosing the initialization smartly, I'll be making sure that the closest local minimum to that initialization is our optimum. Is that what you're doing?
Yeah. Yes, that's right.
Okay.
Yeah, but it's not a local region of convexity, right? So even after I'm close to the thing, the function does not look locally convex. I am close to the. No, it's not flat. It's that we don't have a signal. Okay, one issue is we don't have a single optimum. We have a whole line, and any point on that is optimum.
Yeah,
So I'm close to this line.
it's not strictly convex.
It's not convex. Yeah, even if I'm close to this line, it doesn't look convex there, but it is quite structured. Yeah.
So the points which we are interested to reach are like there's one U star, and any rotation of that U star is a point we would
That's right.
reach here.
Yeah, and
But
any of those points is
but
fine.
Are there other local minimas which are not of that form? It can be, right, depending on the function.
Yeah, so that's a very good question. Okay, so I did not have time to include it here, but so the answer in general I don't know, but if your function is of the form, if your function is separable, so f is summation over ij, fij of xij, right? So it's a sum of terms and each term depends only on one matrix element, right? Then there are actually no bad local minima for any such function.
So, but for those kind of function, you would hope that you don't need a random initialization would work, right?
That is the hope, right? Okay, right. So for here we need to choose a step size more generally, right? So we again do the same thing. We let G be this, and we look at the maximum eigenvalue of the Hessian, right? And the maximum eigenvalue of the Hessian turns out to be this, right? It's M is the strong convexity parameter of F, and X is UU transpose, right? So we can find this spectral norm from U, and we also so this thing in the denominator is the maximum eigenvalue of the Hessian, right? And just as before, we see that even though for f, if you just take the Hessian of f as a Hessian of x, this max eigenvalue is m. Once you have this factored form, the maximum eigenvalue actually depends on the matrix, right? And it depends also on the spectral norm of the gradient, right? So the theorem we have is, I just paraphrased it, but it's we have linear convergence to the optimum contour with this step size from an initial point which is constant distance from the contour. We also have a way to initialize this using the first order oracle, right? So if my only access to the function is the first order oracle, then I have a way to initialize this function. So there are two steps: this initialization and local convergence. This is the local convergence result. For initialization, it depends what we need to think about what we need to do, right? If you only have access to the local to the first order oracle, we have a way to initialize it, but I would say it's not a very good way, right? So what you do is that you take the gradient at 0, right? And you take the negative gradient at 0 and you take its positive definite part, and that would be the initialization. Okay? And there is some reason for that, but that works only for really well conditioned functions, right? So if I had an optimally conditioned function which is just squared loss m minus x square, if I take the gradient at 0, it points directly at x, right? And so I can initialize exactly to the optimum. Now, if my function is not optimally conditioned, then I will make an error that depends on the condition number. And so there will be a range of condition numbers where I will get close enough that my local result works. Okay? So we have that initialization result in the paper. The paper is on arXiv. But in my humble opinion, this is not a good initialization result, right? For initialization, it actually makes sense to somewhat use what you know about f, right? So in the problems I described, that was not the initialization we used, right? We used initialization based on the method of moments, which needs to know the actual what f you're dealing with. Okay, so this is a very recent paper. It's on arXiv. As of Monday, I think, or Sunday. But I think there are many kind of open paths here, and I'm happy to discuss about this. All right. So I think I'll end by saying that there are still many problems where in practice you have fast algorithms which need a low number of samples empirically, but which do not have any guarantees. And often they have corresponding theory which does outline the good statistical assumptions for that problem. And so there are, there's always hope that you can find a principled fast algorithm. So that's what we have been hoping to do. So I think that's it.
Questions?
for the empirical results that you had, like with the matrix completion, is the variance on the practical method versus the theoretical method, are they different? Like is the practical method more variable, for instance, high variance?
High variance.
Yeah, like how many samples it takes to actually recover the true matrix.
Right. So as I said, okay, so we can only answer that question in synthetic settings, right? Which means that I make the, like I know the underlying truth and I make the samples, right? So in synthetic settings, if you have an incoherent matrix and random samples, the non-convex method seems to require fewer samples to get to the same error. So that's the plot I showed there.
Right, but it's still a random matrix that you're creating.
Right. Do you want a universal guarantee?
No, I'm just wondering, like empirically, like what's the variance on the number of samples that it takes?
Or what's the variance in the number of samples? Yeah, that's a good question. I have not recorded that. Yeah, we only record once you get to 95%. In 95% of the instances, it is exactly recovered. Then we record that number of samples. So, yeah, I'm not sure.